Let me go ahead and get the dot cam fired up here and we can get started. Come on, QCam, why are you not listening? Camera's on. No, it's the integrated webcam, no. What's the other thing? Sorry guys, I have to restart the dot cam software. It's been a little glitchy. Close this. Try again. This should work. There it is. Okay, switch on the screen share and we can get rocking and rolling. There it is. So, damn it, really? All right, I'm sorry, I burned through the last of mine. Oh no, we can use this instead. This will be okay. All right, I'm using blue paper today. As promised, this week, we are moving to the next section in chapter 7, after 7.1 on integration by parts, which we covered last week, comes section 7.2, I know, on trigonometric integrals. So hopefully, I think this pen is like a dark purple, but I think it should still contrast. If you have trouble seeing the ink against the blue paper, just let me know and I'll go grab some white paper. I have some downstairs. I'm just being lazy. I don't want to waste time. Okay, so today is the 14th of September, and as promised, we're going to begin. This section usually takes 2 lectures. Section 7.2. And then later this week, we're going to talk about section 7.3, I think also on trig sub. So like I said, this section 7.2, it's a busy section. When I teach it in class, at least the 50-minute classes, I need 2 classes to teach it. The 75-minute classes, sometimes we can knock it out in 1, sometimes we can knock it out in 2. Really, it depends on how comfy you guys are with trig identities. That's the main thing here. Because this section is on trig integrals, which are integrals of trig functions. So the main thing we're going to do here is try to learn how to integrate powers of sine times cosine and powers of secant times powers of tangent. The question about the study guide is a fair question. So is that going to come out this week? We are getting close to the first test, but we're not quite there yet. Partial fractions. Oh, that's how I have it split. So we wanted to do trig integrals last week, but we're doing them this week. Which means that this week we'll be doing trig sub and trig integrals. So we're like half a week behind, basically, because we lost that day to the holiday. So we're about a lecture behind. So we may or may not finish 7.4 this week. The fact that we're starting 7.2 right now tells me that we're probably not going to finish 7.4 this week. And I released the study guide the day we finished the 7.4 lecture, because that's the last main lecture on exam 1. So if we get through 7.4 this week, I will release the first study guide this week. Otherwise, I'll be releasing it next week, and we'll be bumping the exam 1 week back. So that's the most likely thing, I think, to answer your question.
Major?
Yes.
Good morning.
Good morning.
Yeah, so I have some info about homework number 9. Receptive, where they say we can move all the items to one side and get. So I don't understand that one.
Give me just 1 second. So we can look at a homework problem or 2. But while I'm introducing this material, let me go ahead and finish wrapping up the introduction here to section 7.2. All right, so these are the integrals we're going to learn how to do this week. Powers of sine times powers of cosine, and powers of secant times powers of tangent. We can do a few homework problems. But last Friday, we did a handful of homework problems just as a thing to eat up some time. So I don't want to burn too much time on this. So if I don't get to cover the homework problem that you guys wanted to look at right now, then come by my office hour this afternoon. We'll do it then. I know last Friday, I normally have an office hour on Fridays from 2 to 3, but last Friday I had all these meetings that stacked up then. So I wasn't able to do that. So in order to be fair, let's take a look at one of those. Patanji, which one did you want to see?
Homework number 8, question, the question 9.
Question
So where they say
three.
tutorial exercise, and then step 6.
Step 6. Okay. So that was the looping integral, right? Like the e to the something theta times cos of something theta. I'm not sure if I can get in here and look at the individual steps. Let's see. Oh, we can. Okay. Will play nice for me. Step, you cannot submit this. So yeah. So the way you do this integral is by parts, right? If u is sine 6 theta, then du is 6 cos 6 theta. And if dv is e to the 5 theta, then v is e to the 5 theta over 5. It's gonna take a minute, isn't it? So integration by parts says we'll have u times v minus v times du. So that will be e to the 5 theta over 5 times sine 6 theta minus some constant times the integral of e to the 5 theta cos 6 theta. So my v times du integral has what constant pop out? That'll be 6/5. What the fuck? 6/5. And then you want, so is everybody following this? So we wanted to see, I think he said step 6. So step 1, we run IBP. Here we're just calculating du and v to fill out our IBP table. Step 2, they run integration by parts. They ask me to enter the u times v piece. And they've already entered the minus the integral of v times du. They just want me to figure out what constant pops out. So v times du, one of these had a 6, one of them had a 1/5. And now we run IBP one more again. Here we've got u equals cos 6 theta, so du will be negative sine 6 theta over 6, and v, if I integrate that, I still get e to the 5 theta over 5. So the purpose of this problem is to gently walk you through. Why didn't that go? Come on, come on. Maybe I can just skip to it. All right, so 4. So you wanted step 6, you said, right? Let's step 5. Step 6. All right, so we're here. So here's the idea. They want you guys to determine what the constant is that ends up on the far left-hand side here. From this line, what can we say? I've got my 1/5 e to the 5 theta sine 6 theta. That's the original u times v. Minus 6/5 times what I get when I replace this second piece by his integration by parts equivalent. So let me pull over the dot cam here. So just to be clear what we're doing, this is homework 3, problem 9, which was the integral of, in this case, e to the 5 theta cos 6 theta d theta. And we've run some IBP. So I'm going to just put the dot, dot, dots in there. And we get to a place where I find my integral, e to the, let's write it like this. So we get to some place where my integral I is equal to 1/5 e to the 5 theta sine 6 theta minus 6/5 times 1/5 e to the 5 theta cos 6 theta plus 6/5 times my integral. Okay, so we're at this step here. The step Hotanji was wondering about is when I gather all of my copies of my integral on the left-hand side, what's the constant? So if you distribute everything, you'll have I equals 1/5 e to the 5 theta sine 6 theta minus, I'm distributing this 6/5 now, Hotanji. This is what we needed to do. So we'll have 6/5 times 1/5 here. That's 6/25, so that'll be minus 6/25 e to the 5 theta cos 6 theta, and then minus 6/5 times 6/5 I, that's 36/25 times I. So this is the stage where your integral loops, right? You've got your integral equals a bunch of shit minus some constant times your integral. So we're gonna add all of this back over. I'm gonna take this quantity here and add it to both sides. So I'll have I plus 36/25 times I equals all this stuff. 1/5 e to the 5 theta sine 6 theta minus 6/25 e to the 5 theta cos 6 theta. So what they want you to do is figure out this constant over here. And that's going to be 1 plus 36/25 times I. All right, if I factor an I out over here, and that's still equal to all this stuff, which I'm just going to put here some quotes to indicate that this line stays the same. Here, 1 is 25/25, right? So you have to add the numerators, 25 plus 36. Well, if that was 20 plus 30, that would be 50, and then 5 plus 6 is 11, so that's 61/25 I equals, and then that's still that same thing, though, 1/5 e to the 5 theta sine 6 theta minus 6/25 e to the 5 theta cos 6 theta. And then your last step here would be just to divide both sides by this constant. But Hotanji, if you were asking for step 6, this is step 6, right? This constant here is the piece they want right here. And the idea is that you need to distribute this constant, the negative 6/5, across these parentheses, and then take this portion that you'll get, which is this portion, this portion, and add it back over to the other side. So this is the line that they stopped at, or sorry, this is the line that they stopped at in step 6. You distribute this constant, and that gives you my integral equals all this shit minus this constant times my integral. So you add this back over, and you get my integral plus 36/25 times my integral equals all this shit. Factor out the I, and then you're going to divide by this constant, and that will give you your answer. Can I see, use the react, please? Just a thumbs up react if you feel like you would benefit from seeing this problem, this particular problem, homework 3, number 9, worked out in detail. If you were like unable to get through it in a way that made you feel comfortable, if you feel like for whatever reason, more detail is needed than what we saw in lecture last week. Either way, I'm not going to do it right now. I'll like record a video or type out a solution and then post that to Canvas. But if you think you would benefit from that, give me the thumbs up react in Zoom. Just one? Okay, well, maybe then Juan and Zach. See, honestly, I was expecting more than that. Okay, then maybe I'll ask you guys to come by my office hour this afternoon. Maybe Hutanji, Juan, and Zach, if you guys could come through. That way, rather than me having to record and upload a separate video, if there's just those 3 people who want to see it, come by the office hour and I can walk you guys through this. It's the same as the looping integrals we were doing in class. It's just that you have an extra constant here that you have to take care of. So yeah, come by my office hour this afternoon. I would be happy to run through that. And then if you like, we can record that office hour and I could post that video and make it available. But for now, I would like to start talking about the material that we need to talk about this week. Get this out of the way. Like I said, the goal here is to learn how to integrate powers of sine times powers of cosine and powers of secant times powers of tangent. Some prereqs for 7.2. Some shit you gotta know. The Pythagorean identities. This is a trio of trig identities, starting with the most famous, sine squared theta plus cos squared theta. That's always 1. If we divide everywhere here by cos squared, you'll get the next important one, tan squared theta plus 1 equals secant squared theta. And if you were to divide through this first guy, instead of by cosine squared everywhere, by sine squared everywhere, you'll get 1 plus cotangent squared theta equals cosecant squared theta. That third one we don't use quite as much, but the top 2 we're going to use over and over and over again this week. There's also the double and half angle identities. We use a lot of these. The first and simplest double angle identity is sine 2 theta equals 2 sine theta cos theta. We use this a lot. The next double angle identity we don't use anywhere near as often, is cos 2 theta is cos squared minus sine squared. And so these are each called double angle identities because the angle on the left is twice the angle on the right. The next set of identities are called half angle identities because the angle on the left is half the angle on the right. And that's cos squared theta equals 1/2 1 plus cos 2 theta, and then sine squared theta equals 1/2 1 minus cos 2 theta. And there's no typo there. Both of those end in cosines. So these are the trig identities that we're going to use a lot. The ones that we use least among these are this one and this one. Everybody else gets used all the time. So you have to know these cold. You have to know these. Nicholas asked a good question. His question, for anyone who didn't see it in chat, is when are we going to do physical office hours again? And the answer, I actually spoke with my department chair about this very thing just last Friday. The answer is I'm not allowed to do standing physical office hours. So I've been bugging her and requesting rooms and stuff, and the answer keeps coming back no. What I did get permission to do, and this might sound a little bit strange, is even though I can't have regular in-person office hours, if you want to schedule a particular in-person meeting, what we have to do is we have to pitch it like this. The online shit ain't working. All right, the online office hour isn't doing it for me. I just, for whatever reason, it's not working well. I need one in-person office hour, and we can schedule that, and that's okay. We could schedule one of those every week, and that's okay. but I'm not allowed to say I'm going to have an office hour at this time every week. So here's what's up. My wife takes an in-person class Thursdays. And so I think if you wanted to get away with an in-person office hour, the easiest and most subtle way to do it would be to talk to me before the Thursday of a given week. Let me know you want an in-person meeting. I can contact my chair to schedule that. And then we can try to make that go. But we have to be a little bit careful about if we do it too often, we might get in trouble. So let me know if you want to do that. If there's a particular topic that you want to sit down and spend a little bit of time on, actually in person, I can request a classroom so we can stay socially distant, and we can sit there and do some work on a blackboard or whiteboard. So contact me through Canvas or email if you want to do it. I can't do it regularly, but we could do it by appointment, and if those appointments happen to occur regularly, I think that would probably be okay, but we got to try to keep it on the down low. All right, these are the trig identities, but this isn't the only thing that you need to have in your pocket to get going with section 7.2. There's a handful of kind of foundational or fundamental trigonometric integrals that you also need to know. Of course, we know that the integral of sine theta itself is what? Negative cosine theta. Yeah, this is negative cos theta. You know, plus a constant. The integral of cos theta is sine theta. The integral of tangent theta, who remembers this? Anyone remember the integral of the tangent function? That's the derivative, Nick. The derivative of the tangent function is secant squared, but the integral, remember the trick to this is to write it as sine over cosine. And then you substitute for the bottom. You let z be cos theta, so dz is negative sine theta d theta. You get integral negative 1 over z dz. That's negative natural log of z. So this will be negative natural log of cos theta plus a constant. And if it's easier for you to remember, you can bring the negative inside as a power, which would make it the natural log of 1 over cosine, or the natural log of secant theta plus c. So these three, of course, we need to know, right? If we're going to integrate all sorts of combinations of trig functions, integrating sine, cos, and tangent is foundational. There's one other kind of foundational integral here. And that's the integral of the secant function. So the trick to getting here was to sub z equals cos theta. So dz is negative sine theta d theta. And that will get you here. The secant integral is a little bit more complicated. To sort out this guy, we again use u sub. I won't call it u sub, I'll just say substitution. But first, do some clever algebra. So the clever algebra that we need to integrate the secant function, and we should have seen this before. I know I did this in my Calc 1 class at the end. You multiply by secant plus tangent over secant plus tangent. You multiply by 1 in that very strange form. So you get secant theta times secant theta plus tangent theta over secant theta plus tangent theta. So this is kind of like multiplying by the conjugate, right? Where you take something and you want to take a limit of it, or you want to do something nice with it. So you multiply by the conjugate on the top and the bottom. Think of this as being kind of like that. The reason, though, that we do this is because when you distribute, so I'm going to multiply the secant across the top here. So I'll have secant times secant plus secant times tangent. Something very nice happens. I get the integral of secant squared theta plus secant theta tangent theta all over secant theta plus tangent theta. And you might be saying, this looks so much worse than the problem we started with. Why the hell would you ever do this? Fair statement. I inject it here because I imagine many of you are thinking it. If I were to substitute for the bottom, the derivative of secant is secant tangent, and the derivative of tangent is secant squared. So if I were to substitute for the bottom, the top is my differential. So now you let z be secant theta plus tangent theta. dz is then going to be secant squared theta plus secant theta tangent theta d theta. And I'm just writing them in the opposite order like that so you see that it's the top. All right, the derivative of secant is secant tangent. The derivative of tangent is secant squared. But you can do the addition in whatever order you want. So in other words, if you substitute for the bottom, your differential is the top. So all that will be left is 1 over z dz. All right, this is the integral of, I'll write it out, 1 over secant theta plus tangent theta times secant squared theta plus secant theta tangent theta d theta, which is the integral of 1 over z dz. Which is the natural log of z plus a constant, which is the natural log of secant theta plus tangent theta. So that's our last prereq. The integral of secant theta, all on its own, is the natural log of secant plus tangent. So these 4 basic trig integrals you need to know: sine, cosine, secant, and tangent. The sine, cosine, and tangent integrals are all pretty easy. We've definitely done those in the past. The secant integral, depending on your Calc 1 class, I think I don't remember if it was your section or another section. One of my Calc 2 sections, I walked through this already. But in case you haven't seen it before, that's how you integrate the regular secant function. So now you've got the integrals for sine, cosine, secant, and tangent. Those are the building blocks for all the trig functions. The cosecant and cotangent integrals look exactly the same. Just replace each function by their cofunction and put a negative out front. Questions about any of these sort of prerequisite materials?
Excuse me, sir.
Yes.
Yeah, I don't have any question about this. So can you show us how to find the antiderivative of ln s?
Yeah, we did that actually twice in class last week. That's an integration by parts problem. So you run integration by parts with u equal to the natural log of x and dv equal to dx.
Okay, so I can check the video. Don't worry about it.
I'm sorry, I couldn't quite hear that last part. What was the last thing you said?
I said that I'm gonna see the video, the last video, so don't worry about it.
Okay, yeah, review that the last couple videos. We did it, I think, in each one. Honestly, I would suggest going to Wednesday's lecture for that, not Friday's. Wednesday's was the first time we did that, and we did it in some more detail than we did on Friday.
Okay.
All right. So if there aren't any other questions about these trig identities or about these basic trig integrals, then we're going to go ahead and get into 7.2. Any other questions on these identities or basic trig integrals? Okay. So remember what our goal is here. Our goal is to handle integrals that look like powers of sine times powers of cosine or powers of secant times powers of tangent. Because any trig integral can be broken down into combinations of these, right? Through trig identities, the basic ones, the reciprocal identities. I didn't even bother writing those on the previous page because I'm assuming everybody knows those well. Using reciprocal identities, if I give you any mess of trig functions, you can always rewrite it as stuff that looks like this plus stuff that looks like this. So once you know how to do all these integrals, you can do all the trig integrals. That's the idea. We're going to start with the sine times cosine integrals. I'll call it sine m theta cos n theta. When we use m and n in math, we usually use m first because it comes first in the alphabet, but that's the only reason I'm picking that convention. So if one of the powers is odd, if at least one of m or n is odd, then these are easy. We use u sub. We use the first Pythagorean identity. That's sine squared plus cos squared equals 1. And substitution. It'll look something like this. Maybe I want to integrate sine cubed theta times cos to the 4 theta d theta, something like that. So I've got an odd power of sine and an even power of cosine. So is it true that at least one of the powers is odd? Yes, it is. The power of sine is odd. The strategy goes like this. You're going to take one copy of the odd powered guy and set him aside with the differential. So first, I rewrite this as sine squared theta times cos to the 4 theta times sine theta d theta. So first, set aside one copy of the odd powered function. You set it aside with the differential because you're going to make a substitution. In this case, we're going to substitute for cosine. In general, what you'll do is you'll substitute for whatever the other function is. So if you set aside a copy of sine, you're going to substitute for cosine. You set aside a copy of cosine, you're going to substitute for sine. Because that's what you need in the differential to substitute for cosine. Before you do that substitution though, if I wanted to substitute, z equals cos theta, then this piece would be z to the 4. This piece would be negative dz. But what should I do with this? How could I possibly handle that? This isn't a cosine. And the differential is only going to eat up one copy of sine. So the other thing you need to do is rewrite the remaining even powers using the Pythagorean identity. So if you set aside one copy of the odd-powered function, then what's left will always be an even power. And an even power of sine or cosine can always be rewritten as the other guy using the Pythagorean identity, right? Sine squared is 1 minus cos squared. So then we rewrite the remaining, which will be an even powers of the at the start odd powered function using Pythagoras or Pythagorean identity. And now that I'm here, I can substitute for cos theta. So if I sub z equals cos theta, then dz, damn, my pen's dying too. Then dz is negative, up this pen. That's a new thing too. dz is negative, really? Sine theta, d theta. All right, I hope you guys can see that. I'm sorry my pen is acting up. So here I've got 1 minus cos squared times cos to the 4 times sine. That'll be 1 minus z squared times z to the 4 times negative dz. And then you distribute. So then the name of the game here is if at least one of the powers is odd, you can always turn the integral into a polynomial. You can always turn the integrand, the thing you're integrating, into a polynomial. This negative, I'll pop all the way out front. This z to the 4, I'll distribute. So I'll have z to the 4 minus z to the 6 dz. So what we did, we set aside one copy of the odd-powered function, and then we rewrote the remaining even powers using the Pythagorean identity. So here, rewriting sine squared as 1 minus cos squared. Then we substitute for the function that makes sense, right? Substitute for the even powered function. And that'll give us a polynomial. And we always know how to integrate polynomials because that's just a power function thing. So this will be negative z to the 5 over 5 minus z to the 7 over 7 plus c. And because this is an indefinite integral, we tack on the plus c, and then we also have to go back to my original variable. So that will be negative. I'm going to distribute the negative also. Z to the 5 is cos to the 5 theta. And then negative negative here will make plus cos to the 7 theta over 7 plus c. All right, that's it. So as long as one of these powers is odd, life is pretty good. I'll do one more like this, and then I'm going to show you how to handle the case where both powers are even. Questions on this example? Everybody following along okay? Okay, okay. Let's try one more. This time I want you guys to tell me a little bit what to do. Let's do the integral of sine squared times cos cubed. What should I do? Show me just how awake we are. So I have here an even power of sine times an odd power of cosine. So yeah, my very first step should be, before I go rewriting the cosines as sines, Maggie's correct to say we should do that. Before we do that, Nicholas is correct in saying we should take one of these copies of cosine and set it aside. So I'll have sine squared theta times cos squared theta times cos theta d theta. So I take my odd powered function and I set one of them aside. There's two reasons why I'm doing that. First, I want to substitute for sine. This is the differential I'll need to do that. Second, what's left when you set aside one of an odd thing is an even number of things. And since this is an even number of cosines, I can always rewrite them as sines using Pythagoras, like Maggie said. So before I substitute, there's one more thing to do. The sine squared theta comes along for the ride. This cos squared I rewrite as parentheses 1 minus sine squared. And then I've still got this cos theta d theta hanging off the side. And what you see here is that this would be a polynomial if I substituted for sine. That's good. And this is exactly what I need to make that substitution. So at this stage, I let z be sine theta, so that dz is cos theta d theta. That's my, oh, damn this pen, that's my substitution. Under that substitution, my integral becomes integral z squared times 1 minus z squared times dz. Isn't that nice? Then we distribute and integrate. Got to distribute first, of course, because this is multiplication. Integrals don't play nice with multiplication. So you get z squared minus z to the 4. And that'll be z cubed over 3 minus z to the 5 over 5 when you take your antiderivative. And then again, because it's an indefinite integral, we go back to the original variable. So that's sine cubed theta over 3 minus sine to the 5th of theta over 5 plus a constant. Not at all bad, right? Take one copy of the odd guy, set it aside. Then use your trig identities to rewrite whatever is left as a polynomial in the other function. So if you set aside a cosine, your goal is to substitute for sine. That means you need to rewrite the remaining cosines as sines. That's what we did here. I rewrote this cos squared as parentheses 1 minus sine squared. Now that everything over here is sine theta, and over here I've got cos theta d theta, I can substitute z equals sine theta. The cos theta d theta is exactly what I need for my dz, and what's here is a polynomial in sine. So when I substitute for sine, I will get a polynomial. You distribute and rewrite that polynomial in standard form, and then you can integrate. Not at all bad. This is, of all the cases we're going to look at for these trig integrals, the nicest case. All right, before we leave this case, I want to discuss what you do if both powers are odd. So questions on this example, why we did what we did, why it came out like it did, any of that stuff. Everybody has this nice and clean in their notes. Alex asked a good question. How do I know to substitute for sine? You're going to substitute for whatever function you didn't set aside over here. So I started by setting aside a cosine. And that tells me I'm going to substitute for sine. Does that make sense, Alex? Because the differential when you try to substitute for sine is cosine. The differential when you try to substitute for cosine isn't sine, it's negative sine, but it's close enough that that's how it always works. So you start by setting aside a copy of one of these guys, then you'll always substitute for the other. All right, what we haven't seen an example of so far is what do you do if both powers are odd? That was A Q. I don't want to get back to this. Odd numbered years are better years to teach this portion of the class because then I get to insert the current year in the problem. So I'm going to pretend like it's 2021. So what if I wanted to integrate sine cubed times cos to the 2021 theta d theta? Here both powers are odd. So according to the strategy that I've just outlined for you, sorry, James. I'll leave this for just 1 second longer. This one. So while we're finishing writing this, I'll leave this up and we can think about it. Oh, this one? Okay. All right. So if both powers are odd, then you could set aside a copy of either and try to substitute for the other. And it's true that you could solve the problem either way. I could set aside a copy of sine here with the differential, so I'd have sine squared times cos to the 2021 theta times sine theta d theta. Or I could go the other way. I could set aside a copy of cosine, and then I'd have sine cubed times cos 2020 theta times cos theta d theta. And both of those would lead to a successful substitution. It's just that one of them is much harder to integrate. Okay, so I am going to go ahead and continue to this next problem now. If you want to take a look at any of the note pages from the class, of course, we can do that at the end of class too. If you just miss copying something, just leave space in your notes, and at the end of class say, hey, can I take one more look at this page? Focus, you son of a bitch. So here I could set aside a copy of cosine and try to substitute for sine, or I could set aside a copy of sine and try to substitute for cosine. Let me show you how it looks if I set aside a copy of sine. So we're going to do this two ways. we can try to sub for cos theta, which means I'm going to set aside a copy of sine theta. So there I would say my integral is equal to sine squared theta cos 2021 theta times sine theta d theta. Then I rewrite the sine squared as parentheses 1 minus cos squared. And everything else just comes along for the ride. Cos 2021 theta sine theta d theta. And now at this stage, I'm ready to substitute for cosine. There's my substitution. So I'll have integral 1 minus z squared, z to the 2021, negative 1 dz, which is negative integral, distribute the z to the 2021, so I'll have z to the 2021 minus z to the 2023 dz. And this is not hard, right? Power rule. That's negative z to the 2022 over 20, god damn this pen, 22 minus z to the 2024 over 2024 plus c, which would be, and I'll distribute my negative and go back to my original variable, negative cos 2022 theta over 2022 plus cos 2024 theta over 2024 plus c. Okay. So this is how we would solve the problem if we chose to try and substitute for cosine. You want to substitute for cos, that means you set aside a copy of sine and try to rewrite everything else as cosines. That's manageable. It's not hard. And the integral you get out is also not difficult. On the other hand, if I tried to substitute for sine theta, well, then I'm going to set aside one copy of cosine. So I'll have integral sine cubed theta cos 2020 theta times cos theta d theta. That would be integral of sine cubed theta. Now I need to rewrite this cos 2020 as sines. The first step would be to rewrite that as cos squared theta raised to what power? That would be 1010. Right, so if I want to rewrite a large even power of cosine in terms of sines, I need to write it as cos squared raised to some other power. So like cos to the 4 would be cos squared squared. Cos to the 6 would be cos squared cubed. Cos to the 8 would be cos squared to the 4. Cos to the 2020 is cos squared to the 1010. Everybody with me so far? Give me some indication that we're following or not following. Okay, good. this sucks, right? This sucks. This sucks because now I'm going to go ahead and rewrite as sine cubed theta times cos squared. Well, that's 1 minus sine squared. But I got to FOIL that out. God, no. Right? The substitution will still go through just fine. But dealing with this piece is going to be a nightmare. I'll show you what the substitution looks like, but then I'm going to stop. We're not going to finish from this approach because it's horrible. Z here would be sine theta. So dz here would be cos theta d theta. The substitution goes through just fine. And the integral is still a polynomial. It'll be the integral of z cubed times 1 minus z squared to the 1010 dz. But fuck this noise, right? If I wanted to integrate this, I would have to first FOIL this out, then distribute this, then use my power rule. Is it possible? Yeah. Yeah, it is. You have to multiply 1 minus z squared by itself 1010 times. Okay, that's doable, but why? But why when I can do this instead, right? Yeah, you can use the binomial theorem here. Yeah, there are ways to write this thing down, but Nick is precisely correct. No bueno. This is not good. This is deeply unpleasant because I have to distribute this. I have to FOIL this all out before I can distribute this, before I can use the power rule. So FOILing 1 minus z squared to the 1010 would take a little while, to put it mildly. So screw this. All right, so what we have here are two different approaches to solving the same problem, and the reason I'm showing you this is as an extreme example to help you understand what to do in the case where both powers are odd. We said if only one of the powers is odd, you only have one choice. You have to take one copy of that odd guy, set it aside with the differential, substitute for the other guy. If both powers are odd, then your goal should be to substitute for the function with the larger power. What Juan said in chat is exactly correct. So you'll set aside a copy of the smaller powered guy. So if both powers are odd, you could go either way, but you should in your mind want to substitute for the large powered guy, which means you'll set aside a copy of the smaller powered guy and then run the rest of this algorithm. You can try solving some of these problems both ways. I'm not going to give you anything with an enormous power like 2021 in the homework, but I might give you like sine cubed times cos to the 5th, something like that. And those you can run through both ways and get a feel for. Okay, so those are the sine cosine integrals in which at least one of the powers is odd. If one power is odd, one power is even, then you know what to do. Always take one copy of the odd guy, rewrite everything else in terms of the even guy, substitute for the even guy. If both powers are odd, then you have a choice. You should take one copy of the smaller odd guy, set him aside, and then substitute for the large odd guy. So that's it. That's the first part of section 7.2. The second part of section 7.2 deals with the other possibility for these sine cosine integrals. Either one power is odd, one power is even. We've covered that. Both powers are odd. We've covered that. The only other possibility is that both powers are even. Here's a real simple example. Here the power of sine is 2, and the power of cosine is 0. 0 is even. So this does fall into this category. Here, you just use half-angle identities. You don't make any clever substitutions, and you don't use any Pythagorean identities. You just beat these things to death with half-angle identities until they look like something you know how to integrate. So I'll show you what I mean. Sine squared is easy. I rewrite him as 1/2 times 1 minus cos of 2 theta. Remember that half-angle identity from the first page? Then you can either distribute the 1/2 or pull it out. I prefer to pull it out. You got 1/2 integral 1 minus cos 2 theta d theta. Now the integral of 1 is totally trivial. The integral of cos 2 theta, that's a micro u sub. So this is going to be 1/2 theta minus, who could differentiate to cos 2 theta? Well, it's got to be sine 2 theta. But then by the chain rule, if you differentiate sine 2 theta, you'll get a 2 on the outside, so you got to divide by 2. So that's the micro u sub. Integral of cos 2 theta is sine 2 theta over 2. And that's it. You're done. You can distribute the 1/2 if you want. That doesn't look too bad now, does it? Just like with the first case, I'm going to do 2 more examples for a total of 3 examples in each category. The next one I want to look at sine squared times cos squared. The truth is that these are kind of unpleasant. They're not as nice. Maggie, no, unfortunately it doesn't. So the secant and tangent integrals usually, again, we'll break them down into cases based on even and oddness of the powers. But because the derivative of secant isn't tangent and the derivative of tangent isn't secant, we can't do everything exactly the same way we did with sine and cosine. But they do have similar things, right? The derivative of tangent is secant squared, the derivative of secant is secant tangent. So something similar can be applied to some of the secant tangent integrals, but I'll be showing you those once we finish with these. First though, let's finish handling the case where both m and n are even. So if you have just sine squared or just cos squared, then you rewrite those using the half-angle identities, and you do your little micro u sub on the piece that looks like this. If I have sine squared times cos squared, both of them together, then I rewrite both of them using the half-angle identities. So sine squared, that's 1/2 times 1 minus cos 2 theta, and cos squared is 1/2 1 plus cos 2 theta. I'm showing you this additional example here because there are some other little subtleties that can crop up. All right, so 1/2 times 1 minus cos 2 theta, that's sine squared theta. 1/2 times 1 plus cos 2 theta, that's cos squared theta. Now I'm going to gather these constants out front. 1/2 times 1/2 is 1/4, and I'm going to FOIL what's inside. So I'll have 1/4 integral 1 minus cos 2 theta times 1 plus cos 2 theta, like this. And now when I FOIL those, I'll get 1/4 integral 1 minus cos squared 2 theta. the inner and outer terms cancel. It's like a difference of squares. This, however, is no longer a micro u sub because of the square. I can't do it so simply. In fact, the integral of cos squared on its own is a lot like the integral of sine squared on its own. You need another half angle identity. So this is what I meant when I said you need to beat these things to death with the half angle identities. You're going to apply the half angle identities sometimes 3-4 times in one of these problems. Let me pick your brain for just a second here. If cos squared theta is 1/2 1 plus cos 2 theta, then what is cos squared of 2 theta? So I'm saying this to help us deal with this piece. Well, he should be 1/2 times 1 plus the cosine of whatever's here gets doubled here. So whatever's here gets doubled here. Tuck that off to the side. So I'm going to use this version of the half angle identity on this piece. Then I'll distribute and combine like terms. Then I'll be able to finish the integral as micro u subs. This will be 1/4 integral 1 minus, now this cos squared piece here, I write as 1/2 1 plus cos 4 theta, like so. So the 1 comes along for the ride. The minus comes along for the ride. And then cos squared of anything is 1/2 times 1 plus cos of double that thing. All right. Cos squared of 2 theta is 1/2 1 plus cos 4 theta. I'm taking this guy and I'm replacing theta by 2 theta everywhere. So here I get cos squared of 2 theta instead of cos squared of theta. And over here I end up with cos of 4 theta instead of cos of 2 theta. Everybody with me? This piece, just this piece, I replace using this modified half angle identity. So you do really need to be a wizard with your trig identities to survive Calc 2, it's true. So once I have that, now I can distribute this 1/2, and I'll get 1/4 integral 1 minus 1/2 minus 1/2 cos 4 theta d theta. And now I'm happy because there's no more powers of cosine. I can combine the 1 and the minus 1/2, because those are both constant terms. 1 minus 1/2 is 1/2, so I get 1/2 minus 1/2 cos 4 theta d theta. I want to give a word of warning because you might be starting to realize that these trig integrals are not as hunky-dory easy as they might have looked from that first example or first collection of examples, and it's this. these trig identities and these trig integrals are not going away. The next section that we're going to deal with involves taking algebra integrals and turning them into trig integrals. So you got to be really good at these. And then down the road, we'll have other processes that end like this. So you do need to get good at this stuff. Don't back burner this. This is very important. The good news is that now, where we are, now I can do everything with just little micro u subs. The 1/4 out front is going to come along for the ride. 1/2 d theta, he just integrates to 1/2 theta. You don't even need a micro u sub for him. Minus 1/2 times now cos 4 theta, that is a micro u sub. He's going to integrate to sine 4 theta, because who could differentiate to cos 4 theta? It's got to be sine 4 theta. But then by the chain rule, you would multiply by 4. So here when we integrate, our little micro u sub gives us a 4 downstairs. So all together now, if I distribute this 1/4, I'll have 1/8 theta minus, this is going to be 1/8, and then another 1/4 will make 1/32 times the sine of 4 theta plus c. So that's sine squared times cos squared. I could talk about trig integrals for days. If you're interested in harmonic analysis at all, that is things like Fourier series, which are hugely important, not just in like signal processing and sound design, but surprisingly disparate parts of physics and engineering use a lot of Fourier series. They're all built around integrals like these. So these are, like I said, hugely important. Yeah, I can bring this back up for just one more second here. This is our regular half angle for cosine. And all I did is everywhere there was a theta here, I wrote 2 theta here. So cos squared theta becomes cos squared of 2 theta. 1/2 1 plus cos 2 theta becomes 1/2 1 plus cos 2 times 2 theta is 4 theta. Okay. Yeah, and this is where we're going to have to pull the plug for today. Unfortunately, we are out of time, which means the secant tangent integrals will have to wait until Wednesday. So the secant tangent integrals, again, they break down according to cases. There's 2 easy cases, and then there's a hard case there. The easy cases look a lot like the easy case here, which was the case where one of the powers is odd. Before I let you go, I have the textbook here, you should read section 7.2. So they say everything I said in a little bit more detail, and they do more examples, and you can look at these examples, and this will be good for you. You should do that. I would encourage you to also read, so here's the general description. If one of these powers is odd, rewrite, and then substitute for the other guy. So if the power of cosine is odd, you're going to substitute for sine after rewriting everything else as sines. If the power of sine is odd, you're going to substitute for cosine after rewriting everything else as cosines. And if the powers are even, you beat the things to death with these 2 identities. The secant tangent integrals are a little different. You can kind of sniff your way through them using u sub and the Pythagorean identities, except in the case where the power of secant is odd, and they don't discuss it here, except in the case where the power of secant is odd and the power of tangent is even, right? If the power of secant is even, then we can do something similar to the sine cosines. If the power of tangent is odd, we can do something similar to the sines and cosines. For all other cases, and those other cases are where the power of secant is odd and the power of tangent is even, then you're going to use integration by parts. And in general, they will be looping integrals. So next time, that's what we're going to look at. I'm going to show you how to do all the secant tangent integrals. And keep in mind then, if you want to work ahead in the homework, if you bump into a secant tangent integral where the power of secant is odd and the power of tangent is even, save that. And just save that until after Wednesday, because those are going to be looping integrals that are going to require, they say, a little ingenuity. It's not that bad. It's going to be a lot like the integral of secant cubed I showed you last week, only perhaps with more trig identities. So please read section 7.2 in the textbook, take a look at their examples, and take a look at the first few homework problems. I'll be popping open your homework 4 in a little bit. If you need more time on homework 3, submit an extension request. I'll be plowing through those as soon as I finish with my next class. And then that is it for today, lads and ladies. I hope that this felt tractable. Did anybody need to see any of these notes real quick before I go? Any pieces that we didn't get copied or anything else that we wanted to see? Oh, I see something there. Okay, cool. Alrighty then, I'm gonna go ahead and end the meeting here for the day. I will see you guys on Wednesday or in office hours this afternoon. I do have my normal office hour this afternoon. Take care.